When dealing with electrical circuits, especially over long distances, selecting the correct wire gauge is essential to ensure safe and efficient operation. In the specific scenario of a 20-amp circuit running a distance of 250 feet, the primary concern is voltage drop. The National Electrical Code, or NEC, sets standards to maintain voltage drop within acceptable limits, generally stipulating a maximum voltage drop of 5% for branch circuits. Voltage drop refers to the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause various problems, including reduced performance of electrical equipment, overheating of conductors, and potential safety hazards. To determine the appropriate wire gauge for a 20-amp circuit running 250 feet, we need to consider the factors that influence voltage drop. These include the amperage of the circuit, the length of the run, and the resistance of the conductor. Firstly, the higher the amperage, the greater the voltage drop. Secondly, the longer the run, the greater the voltage drop. Thirdly, the higher the resistance of the conductor, the greater the voltage drop. The resistance of a conductor is inversely proportional to its cross-sectional area. This means that a larger wire gauge, such as 6 AWG, has a lower resistance than a smaller wire gauge, such as 8 AWG. The NEC provides tables and formulas to calculate voltage drop for different wire gauges and circuit conditions. These calculations take into account the conductor material, temperature, and other factors. According to standard voltage drop calculations, using 8 AWG copper wire for a 20-amp circuit running 250 feet would result in a voltage drop of approximately 4.5%. This is within the NEC recommended limit of 5%. On the other hand, using 6 AWG copper wire would result in a voltage drop of approximately 3.2%. This is also within the acceptable limit. While both 8 AWG and 6 AWG wires would technically meet the NEC requirements for voltage drop in this scenario, it is generally recommended to use a larger wire gauge, which is 6 AWG for long circuit runs. This is because using a larger wire gauge provides a greater margin of safety and helps to minimize the risk of voltage drop issues in the future. In addition to voltage drop considerations, there are also other factors to consider when selecting the appropriate wire gauge for an electrical circuit, including the ampacity of the wire. Ampacity refers to the maximum amount of current that a conductor can safely carry without overheating. The NEC provides tables that specify the ampacity of different wire gauges based on the conductor material and insulation type. For example, 8 AWG copper wire typically has an ampacity of around 40 amps, while 6 AWG copper wire typically has an ampacity of around 55 amps. In the case of a 20-amp circuit, both 8 AWG and 6 AWG wires would have sufficient ampacity to safely carry the current. However, it is important to ensure that the wire gauge selected is appropriate for the specific application and that it meets all applicable NEC requirements. It is also important to consider the type of load that the circuit will be serving. For example, if the circuit will be serving a motor load, it may be necessary to use a larger wire gauge to account for the motor's inrush current. Inrush current refers to the high amount of current that a motor draws when it is first started. This inrush current can cause a significant voltage drop, which can affect the motor's performance and lifespan. In addition to the above considerations, it is also important to follow all applicable electrical codes and regulations when installing electrical wiring. These codes and regulations are designed to ensure the safety of people and property and to prevent electrical hazards. It is always recommended to consult with a qualified electrician to determine the appropriate wire gauge and wiring methods for a specific electrical installation. Electricians have the knowledge and experience to assess the specific conditions of the installation and to make informed decisions that will ensure a safe and reliable electrical system. In summary, for a 20-amp circuit running 250 feet, 8 AWG copper wire is generally considered to be an acceptable size, as it will result in a voltage drop that is within the NEC recommended limit of 5%. However, using 6 AWG copper wire would provide a greater margin of safety and would help to minimize the risk of voltage drop issues in the future. Ultimately, The best wire gauge for a specific application will depend on a variety of factors, including the amperage of the circuit, the length of the run, the type of load being served, and all applicable electrical codes and regulations. Consulting with a qualified electrician is always recommended to ensure a safe and reliable electrical installation. Firstly, consider the length of the circuit run. Longer runs result in greater voltage drop, requiring a larger wire gauge to compensate. Secondly, examine the amperage of the circuit. Higher amperage circuits experience more voltage drop, necessitating a larger wire gauge. Thirdly, refer to the NEC tables for ampacity and voltage drop. These tables provide guidance on selecting the appropriate wire gauge for various circuit conditions. Fourthly, account for the type of load the circuit will serve. Motor loads, for example, may require larger wire gauges due to inrush currents. Fifthly, factor in environmental conditions. High temperatures can affect wire ampacity, requiring adjustments to wire gauge selection. Sixthly, consider future load growth. Selecting a larger wire gauge than currently required can accommodate future increases in electrical demand. Seventhly, ensure compliance with all applicable electrical codes and regulations. These codes are designed to ensure safety and prevent electrical hazards. Eighthly, consult with a qualified electrician. Electricians have the expertise to assess specific installation conditions and recommend appropriate wire gauges. Ninthly, use a voltage drop calculator. These calculators can help determine the expected voltage drop for various wire gauges and circuit parameters. Tenthly, prioritize safety and reliability. Selecting the appropriate wire gauge is crucial for preventing overheating, voltage drop issues, and other electrical hazards. The decision between 6 AWG and 8 AWG wire for a 20 amp circuit spanning 250 feet hinges primarily on voltage drop calculations and adherence to the National Electrical Code, or NEC, guidelines. The NEC recommends limiting voltage drop to a maximum of 5% in branch circuits to ensure efficient and safe operation of electrical equipment. Firstly, consider the voltage drop. Voltage drop is the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can lead to inefficient operation of electrical devices, overheating of wires, and potential equipment failure. Secondly, perform voltage drop calculations. Use online calculators or the NEC recommended formulas to calculate the voltage drop for both 6 AWG and 8 AWG wire over a 250-foot distance with a 20 amp load. Factors such as conductor material, typically copper or aluminum, and operating temperature influence these calculations. Thirdly, compare calculated voltage drops to the NEC limit. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. Ensure that the calculated voltage drop for the chosen wire gauge falls within these limits. Fourthly, evaluate the ampacity of the wires. Ampacity refers to the maximum current a conductor can safely carry without exceeding its temperature rating. The NEC specifies ampacity ratings for different wire gauges and insulation types. Ensure that both 6 AWG and 8 AWG wires have sufficient ampacity to handle the 20 amp load. Fifthly, consider the cost difference. 6 AWG wire is typically more expensive than 8 AWG wire due to its larger size and greater amount of copper. However, the cost difference may be negligible compared to the potential consequences of using an undersized wire. Sixthly, factor in future expansion. If there's a possibility of increasing the load on the circuit in the future, using 6 AWG wire provides a greater margin of safety and reduces the likelihood of needing to upgrade the wiring later. Seventhly, assess the installation environment. Factors such as ambient temperature, conduit fill, and insulation type can affect the ampacity and voltage drop characteristics of the wires. Ensure that the chosen wire gauge is suitable for the specific installation environment. Eighthly, check local electrical codes. Local electrical codes may have additional requirements or restrictions regarding wire size and voltage drop. Consult with a qualified electrician or local building inspector to ensure compliance with all applicable codes. Ninthly, consider the type of load. The type of load connected to the circuit can influence the voltage drop and wire size requirements. For example, motor loads typically require larger wire gauges due to their high inrush currents. Tenthly, prioritize safety and reliability. Ultimately, the decision of whether to use 6 AWG or 8 AWG wire should be based on ensuring the safety and reliability of the electrical system. If there is any doubt, it's always best to err on the side of caution and use the larger wire gauge. In a context of a 20 amp circuit extending 250 feet, the selection between 6 AWG and 8 AWG wire necessitates a comprehensive understanding of voltage drop, ampacity, and adherence to the National Electrical Code, or NEC. Firstly, voltage drop emerges as a pivotal consideration. Voltage drop signifies the diminution of voltage along a conductor's length due to its inherent resistance. Excessive voltage drop can precipitate a cascade of issues encompassing diminished equipment performance, conductor overheating, and potential safety hazards. The NEC stipulates a voltage drop limit of 5% for branch circuits, underscoring the criticality of meticulous wire gauge selection. Secondly, meticulous voltage drop calculations are indispensable. These calculations entail the utilization of online tools or NEC recommended formulas to ascertain the voltage drop for both 6 AWG and 8 AWG wire across the specified 250-foot distance, while accommodating the 20 amp load. Factors such as conductor material, typically copper or aluminum, and operating temperature exert influence over these calculations, warranting careful attention. Thirdly, comparison against NEC limits is paramount. The calculated voltage drops for both wire gauges must be juxtaposed against the NEC prescribed limits, ensuring that the chosen wire gauge adheres to the regulatory framework. The NEC advocates a maximum voltage drop of 3% for branch circuits and 5% for feeders, serving as benchmarks for compliance. Fourthly, ampacity assessment assumes significance. Ampacity denotes the maximum current a conductor can safely convey without surpassing its temperature threshold. The NEC furnishes ampacity ratings for diverse wire gauges and insulation types, mandating that both 6 AWG and 8 AWG wires possess adequate ampacity to accommodate the 20 amp load. Fifthly, cost considerations warrant attention. 6 AWG wire typically commands a higher price point compared to 8 AWG wire, attributable to its larger dimensions and increased copper content. However, the cost differential must be weighed against the potential ramifications of utilizing an undersized wire, ensuring a judicious allocation of resources. Sixthly, anticipation of future expansion is prudent. Should there be a foreseeable prospect of augmenting the circuit's load in the future, opting for 6 AWG wire offers a heightened safety margin and mitigates the likelihood of subsequent wiring upgrades, thus optimizing long-term infrastructure resilience. Seventhly, installation environment evaluation is imperative. Environmental variables such as ambient temperature, conduit fill, and insulation type can impinge upon the ampacity and voltage drop characteristics of the wires, necessitating a thorough assessment of the installation milieu. Eighthly, adherence to local electrical codes is non-negotiable. Local electrical codes may impose supplementary requisites or constraints pertaining to wire size and voltage drop, underscoring the importance of consulting with a qualified electrician or local building inspector to ensure comprehensive compliance. Ninthly, load type analysis is crucial. The nature of the load connected to the circuit can influence voltage drop and wire size specifications. For instance, motor loads typically necessitate larger wire gauges to accommodate their elevated inrush currents, thereby averting performance degradation. Tenthly, prioritization of safety and reliability is paramount. The ultimate determination of whether to employ 6 AWG or 8 AWG wire should be predicated on ensuring the safety and reliability of the electrical system, with a bias towards caution and the selection of the larger wire gauge in cases of uncertainty. When faced with the decision of choosing between 6 AWG and 8 AWG wire for a 20 amp circuit extending 250 feet, several factors should be taken into consideration to ensure safety and compliance with the National Electrical Code, or NEC. Firstly, it's essential to understand the concept of voltage drop, which refers to the decrease in voltage along the length of a wire due to its resistance. The longer the wire and the higher the current, the greater the voltage drop. The NEC recommends limiting voltage drop to no more than 5% for branch circuits to ensure proper operation of electrical equipment. Secondly, calculations should be performed to determine the voltage drop for both 6 AWG and 8 AWG wire over a 250-foot distance with a 20 amp load. Online voltage drop calculators or NEC tables can be used for this purpose. Factors such as wire material, copper or aluminum temperature, and whether the wiring is in conduit or open air can affect the results. Thirdly, the calculated voltage drop for each wire size should be compared to the NEC recommended limit of 5%. If the voltage drop for 8 AWG wire exceeds this limit, then 6 AWG wire should be used to ensure compliance and prevent potential problems. Fourthly, ampacity, which is the maximum current a wire can safely carry without overheating, should be considered. The NEC specifies ampacity ratings for different wire sizes and insulation types. Both 6 AWG and 8 AWG wire typically have ampacity ratings that exceed 20 amps, so ampacity is less of a concern in this scenario than voltage drop. Fifthly, the cost difference between 6 AWG and 8 AWG wire should be weighed against the benefits of using the larger wire size. 6 AWG wire is typically more expensive due to its larger size and greater amount of copper. However, the cost difference may be justified if it ensures compliance with the NEC and prevents potential problems caused by excessive voltage drop. Sixthly, future needs should be taken into account. If there's a possibility that the load on the circuit will increase in the future, it may be wise to use 6 AWG wire to provide a greater margin of safety and avoid the need to rewire the circuit later. Seventhly, the type of load being served by the circuit should be considered. Certain types of loads, such as motors, may be more sensitive to voltage drop than others. If the circuit is serving a motor or other sensitive equipment, it may be more important to minimize voltage drop by using 6 AWG wire. Eighthly, local electrical codes and regulations should be consulted to ensure compliance. Some local jurisdictions may have stricter requirements for voltage drop or wire size than the NEC. Ninthly, the advice of a qualified electrician should be sought. An electrician can assess the specific circumstances of the installation and provide recommendations based on their expertise and knowledge of local codes. Tenthly, safety should always be the top priority. If there's any doubt about which wire size to use, it's always best to err on the side of caution and use the larger wire size to ensure a safe and reliable electrical installation. The question of whether to use 6 AWG or 8 AWG wire for a 20 amp circuit running 250 feet is a common one in electrical work, and the answer depends on several factors, primarily related to voltage drop and adherence to the National Electrical Code, or NEC. Firstly, understanding voltage drop is crucial. Voltage drop is the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause lights to dim, motors to run inefficiently, and electronic equipment to malfunction. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Secondly, calculate the voltage drop for both wire sizes. Several online voltage drop calculators are available, or you can use the formula voltage drop equals 2 times K times I times D divided by circular mils, where K is the constant for the conductor material, 12.9 for copper, I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor. For 8 AWG copper wire, the circular mils is 16,510, and for 6 AWG copper wire, it's 26,240. Thirdly, compare the calculated voltage drop to the NEC recommendations. If the voltage drop exceeds 3% for a branch circuit or 5% for a feeder using 8 AWG wire, then 6 AWG wire should be used to reduce the voltage drop to an acceptable level. Fourthly, consider the ampacity of the wire. Ampacity is the maximum current a conductor can safely carry without overheating. The NEC provides ampacity tables for different wire sizes and insulation types. Both 6AWG and 8AWG copper wire typically have ampacity ratings that exceed 20 amps, so ampacity is usually not the primary concern in this scenario. Fifthly, factor in the cost difference between the two wire sizes. 6AWG wire is more expensive than 8AWG wire due to its larger size and greater amount of copper. However, the cost difference should be weighed against the benefits of using the larger wire size, such as reduced voltage drop and improved performance of electrical equipment. Sixthly, think about potential future needs. If there's a possibility that the load in the circuit will increase in the future, it may be wise to use 6AWG wire to provide a greater margin of safety and avoid the need to rewire the circuit later. Seventhly, take into account the type of load being served by the circuit. Some loads, such as motors and electronic equipment, are more sensitive to voltage drop than others. If the circuit is serving a sensitive load, it's more important to minimize voltage drop by using 6AWG wire. Eighthly, consult local electrical codes and regulations. Local codes may have stricter requirements for voltage drop or wire size than the NEC. Ninthly, seek advice from a qualified electrician. An electrician can assess the specific circumstances of the installation and provide recommendations based on their expertise and knowledge of local codes. Tenthly, prioritize safety and reliability. If there's any doubt about which wire size to use, it's always best to err on the side of caution and use the larger wire size to ensure a safe and reliable electrical installation. When addressing the question of whether to utilize 6AWG or 8AWG wire for a 20 amp circuit spanning 250 feet, a multitude of factors demand careful consideration, primarily revolving around voltage drop and adherence to the National Electrical Code, or NEC. Firstly, a comprehensive grasp of voltage drop is paramount. Voltage drop manifests as the reduction in voltage along the conductor's length attributable to its inherent resistance. Excessive voltage drop precipitates a cascade of deleterious effects, encompassing diminished light intensity, compromised motor efficiency, and potential malfunction of electronic equipment. The NEC advocates a voltage drop limitation of 3% for branch circuits and 5% for feeders, underscoring the criticality of precise wire gauge selection. Secondly, meticulous calculation of voltage drop for both wire sizes is indispensable. Employing readily available online voltage drop calculators or leveraging the formula voltage drop equals 2 times K times I times D divided by circular mils, where K denotes the constant for the conductor material, typically 12.9 for copper, I represents the current in amps, D signifies the one-way distance in feet, and circular mils denotes the cross-sectional area of the conductor, is imperative. For 8AWG copper wire, the circular mils value is 16,510, while for 6AWG copper wire, it registers at 26,240. Thirdly, a comparative analysis of the calculated voltage drop against NEC recommendations is essential. If the voltage drop surpasses 3% for a branch circuit or 5% for a feeder when employing 8AWG wire, transitioning to 6AWG wire becomes imperative to curtail voltage drop to an acceptable threshold. Fourthly, the ampacity of the wire merits meticulous scrutiny. Ampacity denotes the maximum current a conductor can safely bear without succumbing to overheating. The NEC furnishes ampacity tables delineating the permissible current carrying capacity for diverse wire sizes and insulation types. Given that both 6AWG and 8AWG copper wire typically exhibit ampacity ratings exceeding 20 amps, ampacity assumes secondary importance compared to voltage drop considerations in this context. Fifthly, economic implications stemming from the disparity in cost between the two wire sizes necessitate careful evaluation. 6AWG wire commands a higher price point compared to 8AWG wire, attributable to its larger dimensions and augmented copper content. However, the cost differential must be judiciously weighed against the attendant benefits of employing the larger wire size, encompassing reduced voltage drop and enhanced performance of electrical equipment. Sixthly, anticipation of potential future needs warrants consideration. should there be a foreseeable prospect of escalating the load on the circuit in the future. Opting for 6 AWG wire proactively furnishes a greater safety margin and obviates the exigency of subsequent rewiring endeavors. Seventhly, the nature of the loads served by the circuit assumes significance. Certain loads, notably motors and electronic equipment, exhibit heightened sensitivity to voltage drop compared to others. In instances where the circuit caters to such sensitive loads, prioritizing the minimization of voltage drop through the adoption of 6 AWG wire becomes paramount. Eighthly, adherence to local electrical codes and regulations is non-negotiable. Local codes may stipulate more stringent requisites pertaining to voltage drop or wire size compared to the NEC, underscoring the importance of meticulous compliance. Ninthly, seeking counsel from a qualified electrician is advisable. An electrician possesses the requisite expertise to assess the specific nuances of the installation and proffer recommendations grounded in their proficiency and familiarity with local codes. Tenthly, prioritizing safety and reliability remains paramount. In instances of uncertainty regarding the optimal wire size selection, adopting a conservative approach and opting for the larger wire size is prudent to ensure safe and dependable electrical installation.